Thank you. Could you bring up the first slide, please? So I will be talking about gravity and warped space-time. Warped in English, it's also a word not often used in English in this context. It means distorted or curved. Our first deep understanding of gravity came from Isaac Newton in 1687 in his famous book, The Principia. He postulated that gravity is a pull, a force by which a heavy object such as the Earth pulls on a smaller object such as the Moon, and the force is proportional to 1 over the square of the distance between the Earth and the Moon, or between the object and the heavy body that pulls. With that postulate, he was able, using mathematics, to explain very quantitatively the gravity that we feel on the surface of the Earth, the orbits of the planets and comets around the Sun, the orbits of moons around the planets, and even now that we know about galaxies, the motions of galaxies around each other. This was a remarkably successful theory to explain a wide range of phenomena. But Albert Einstein in 1912 declared that Newton must have been wrong. And he declared this without any significant experimental evidence or observational evidence. The reason he said this is because he had developed what was called the special theory of relativity, which explained to us that the distance between two objects is different depending on who measures it. If the objects are moving relative to each other, as the Earth and the Moon do, then the Earth and the Moon will disagree about that distance. And because Newton's entire framework for the laws of nature insisted that distance is a universal concept, it doesn't depend on who makes the measurement, the very foundations of Newton's theory of gravity were gone, and Einstein said we have to invent a new way of thinking about gravity. The Earth and the Moon disagree about the distance, therefore Newton must be wrong. And so Einstein then embarked on his general theory of relativity, in which he said already just 100 years ago in 1912, as a first step toward general relativity, that the Earth's mass slows the flow of time by about 1 second in 100 years. That is, if you're on the surface of the Earth, then you will age more slowly than if you were up at very high altitude, more slowly by 1 second out of 100 years. That's not much difference. But that was enough to explain gravity, because Einstein then went on to say everything wants to live where it will age most slowly, and gravity pulls it there. And he wrote down a formula which explained mathematically how you got precisely the same gravitational forces as Newton had predicted. It's the same as we measure out of this very, very small difference in the rate of flow of time, the rate of aging. In fact, this warping or slowing of time, although Einstein insisted it was there, it was not measured until about 50 years later. And at that time, it was measured with a precision of about 10% accuracy. Today, it has been measured with a precision of 1 part in 10,000, remarkably good precision. But today, now 100 years later, in fact, it is part of everyday technology. The global positioning system, by which clocks and satellites that are orbiting around the Earth send signals down to your GPS device. Your device has a computer that computes where you are on the Earth to high precision. This would not work if the computer failed to correct for the fact that time flows more rapidly at the location of the satellites than on the surface of the Earth. So this is part of your GPS system, Einstein's law of time warps, the slowing of time. Einstein also, in his general theory of relativity, declared that space is warped. Not just time slowed, but space is warped inside and around the sun and other massive bodies. If you take the sun and you construct an equatorial slice through the sun, the geometry of that slice will not be the same as the geometry of the top of your table. It will not be flat. It will not be the geometry that that Euclid explored. But rather it will be curved. It will be the geometry of a bowl like this. The circumference around the sun will not be pi times its diameter. It will be less than pi times the diameter, less by a few kilometers. It's a small amount, but it's very fundamental conclusion. And in fact, Einstein then went on to say, if we look at the position of stars on the sky at a time when the sun is between these two stars, so you must do this in a solar eclipse, and if the stars are at this true location, then the light rays will travel through the warped space and come back out, and it will appear that this star is displaced outward from its true location by about 2 seconds of arc. Very, very small amount, but enough to be measured. So if the sun is present and you measure the locations of these stars in an eclipse, you will discover that they appear to be out here, whereas if you measure the locations in the absence of the sun, not during the eclipse, 6 months away, then they are at this location. And so in 1919, such a measurement was made during an eclipse, and this was a great triumph that made Einstein famous, made him a world icon for science. Today, this effect has been measured again to an accuracy of about 1 part in 10,000. So we know that Einstein was right to very, very high precision. There was another prediction. This one was actually found not by Einstein, but by 2 people named Lenz and Thirring in 1919. But working with Einstein's equations of his general relativity, they made the following prediction: that as the Earth turns on its axis with 1 revolution per day, it will actually drag space into motion around the Earth, much more slowly in this case. 1 revolution in 6 million years, but space will actually move around the Earth, pulled by the rotation of the Earth. This was actually measured by a gyroscope in a satellite above the Earth, gravity probe B in 2006, to about 15% accuracy. So we know again that Einstein was right, though the accuracy of the measurement is not so good in this case. This dragging of space into motion is going to be very important for what I will tell you in the next few minutes. I want now, having explained to you, there are 3 aspects of the warping of space and time. There's slowing of time, there's a warping of the shape of space, there's a pulling of space into motion. I want to describe what this tells us about the distant universe, about situations that are much more extreme than what we have in our solar system. 1939, Robert Oppenheimer, just a few years, just shortly before the outbreak of the Second World War, he did a calculation with a student named Hartland Snyder of what would happen if you have a large star. It exhausts the nuclear fuel inside itself that are keeping it hot. The star, no longer able to remain hot, begins to shrink. It can't keep itself puffed out to large size. It shrinks smaller and smaller. And the calculation, as it gets smaller, gravity at the surface gets stronger. The slowing of time at the surface gets stronger. It gets smaller and smaller. And ultimately, it becomes so small that gravity becomes so strong that nothing can get out. Time slows to a halt. It can no longer flow at the surface. And this is a black hole. The star creates a black hole around itself as it continues to shrink. We now know that there are millions of these black holes in our galaxy. There are trillions in the universe. But that's still not a lot. The closest black hole is still about 100 light years away. It would take 100 years for light to go from the black hole to us if the black hole were to produce light, which it cannot do. The black hole, in fact, is not made out of the matter of the star that created it. The matter has now been destroyed in the center of the black hole. The black hole is made entirely from warped space and warped time. It's what we call sometimes a soliton. This is a technical term. It's an object that holds itself together through its own energy. The energy of the warping produces the warping of space and time, to be a little bit technical. And so in particular, if you look at the circumference of the black hole and then compare it with the diameter is actually very large compared to the circumference. You can understand this from the following analogy. Suppose I take a rubber sheet or a child's trampoline. I put a very heavy rock at the center so the rubber is bent down like this. Now suppose that you are an ant. You live on this trampoline. The trampoline is your entire universe. You're a blind ant. You can't see. And so you don't see the rock. You don't see the bending shape. But you're a very intelligent ant. You have studied at the University in Vienna or at the ETH. And so you say, I will measure the geometry of my universe. And so you march around and measure the circumference, and then you go to measure the diameter, and you have to travel a very great distance to get to the other side. You discover the diameter is very large compared to the circumference, and you declare, I live in a warped universe. I do not live in a universe that obeys the laws of Euclid. My universe is warped. The very same diagram describes the equatorial slice through a black hole. I just changed the labels. We are now looking in at this black hole from a higher dimensional space that I call hyperspace. Sometimes physicists use a strange other name for it, the bulk they use as a name. But we look in from a higher dimensional space and we can see that the space of the black hole is bent down like that the center is a singularity where the warping is infinitely strong, and I will explain this in a few minutes. Again, the diameter is very large compared to the circumference. We also know that if I fall into a black hole, I can't get out, and signals cannot get out. So here there's a picture of me. I'm traveling down this surface. Remember, only the surface is part of our universe. The third dimension is a higher dimensional universe in which we live, a hyperspace. So I show a two-dimensional Kip falling into a black hole, transmitting a signal out with a microwave transmitter. When I fall below the surface of the black hole, the signals and I get pulled into the center, into the singularity, where I die. I pay the ultimate price that I can't publish the results of my observations because I can't get the signals out from inside the black hole. The surface of the black hole is called its horizon because if you're on the outside, if you're here, you cannot see beyond the horizon. And so the horizon is the place beyond which we can't see the interior of the black hole. So the black hole has its warped space. It has the singularity at the center. It has a warping of time. Time slows as you near the horizon. If you're just a few meters above the horizon, time flows so slowly that you could go there and stay there for one day and return to Earth, and 1,000,000 years may have passed on Earth. But you aged by only one day, while 1,000,000 years passed on Earth. If you are right at the horizon, time slows to a halt. It doesn't flow at all, but you can't stay there because of the pull. You are pulled on in, and now time flows in a direction that is toward the singularity. This is not a space direction, even though it looks like it on the picture. It's a time direction. And this is why nothing can get out from inside a black hole. Nothing can move backward against the flow of time. So everything is pulled by the flow of time into the singularity. And that gravitational pull, once again, governed by Einstein's law of time warps, it's infinitely strong because time is slowed so strongly at the horizon. As the black hole spins on its axis, it drags space into motion very strongly now. So if you're near the surface of a black hole, you're dragged around and around relative to the distant stars at a rate that may be many times per second. You go around and around a black hole because of space is dragged into motion. If you fall into the singularity, you will discover, according to Einstein's laws of general relativity, you'll discover that it's very unpleasant. You get stretched from head to foot and squeezed from the sides as you near the center. But that only briefly. A moment later, you are stretched from the sides and squeezed from head to foot. And then back to this direction of stretch and squeeze. And this goes faster and faster in a very chaotic way until ultimately your body is torn apart. And then the atoms from which your body are made are torn apart. And then you hit the singularity, and we don't know what happens then, because this is governed by a new set of physical laws called the laws of quantum gravity, which come by combining Einstein's relativity theory with the laws of quantum physics. The effort to combine those is the best approach to this is what is called string theory. String theory is making much progress. It's sometimes also called M theory. These are fancy terms for these new laws of quantum gravity. I think within the next 10 to 20 years, we may understand these well enough that it will tell us what happens at the very location of the singularity. But if you fall in, you are dead long before you get there. So this is more of a theoretical, but a deep theoretical question. I'd like now to describe where we stood in our study of warped space and time about 5 years ago. And then I will describe my current research directions, what I'm doing to understand new aspects of warped space and time. I'm going to do this by an analogy. Before Columbus, we believed the ocean was flat, the world was flat. The same way before Einstein, we believed that space, three-dimensional space, was flat, like Euclid described, and that time flowed uniformly at the same rate everywhere. After Columbus, we understood the Earth and its oceans are spherical. After Einstein, we understood that space is warped, time is warped, and that you can have black holes. What I would like to understand, and that we have not yet understood for space and time, is what happens in a storm. In a storm on the ocean, you have violent motion of the surface of the ocean. You have waves. And what happens when space and time are in a storm? When you have violent motion of the flow of time, when the space, the three dimensions of space in which we live, have crashing waves like in a storm. That's the direction of my current research. I'm going to show you here an artist's conception from some years ago before we had an understanding of the answer. This is the situation where where we are exploring how space and time behave in a storm. Two black holes orbiting around each other. I've cut off these diagrams at the horizon of the black holes. And so you see each black hole. Here's another picture where looking from greater distance, and you see that as the black holes go around each other, they create waves in the surface of space, the waves in the shape of space, like waves on Lake Constance if you put your hand in and you stir around in the lake. These are called gravitational waves. That's the technical word for them. As the two black holes go around and emit waves, they lose energy, and this causes them to spiral together and collide and merge into one black hole. And these waves go out carrying information about this process. Now, this is a very violent process. So violent that the power that comes out during this collision. That's the energy that comes out in a unit amount of time. In these gravitational waves is 10,000 times more than the total luminosity, the total power from all the stars in the universe put together, coming from one collision of two black holes. If the black holes are small, the collision is fast, and so the total energy that comes out, it's the product of this huge power times a short moment of time. The total energy is fairly small. It's 10% of the mass of those two black holes. If the black holes are huge, the collision is longer, there's more energy comes out, but it's still 10% of the mass of those two black holes. But this is just one number that tells you that these are the most violent events in the universe except the birth of the universe itself. And the details of the collision that I would like to understand are encoded in the shapes of the waves that come out. And so I will describe for you in a few minutes a project to detect these waves, measure the shapes of the waves, from the shapes of the waves to extract the information about what is happening in this storm, in this violent event. Each black hole drags space into motion, so these black holes are like two tornadoes of whirling space. The orbital motion of the black holes around each other also drags space, so we actually have two tornadoes inside a third larger tornado. And we want to know what happens when they come crashing together, when the tornadoes are made from whirling space instead of whirling air. And so that is the challenge, and we have been obtaining the answer in the last 2 years through numerical simulations on computers. So I'm going to show you a movie from a numerical simulation on a computer of two black holes. This is not a very interesting case because the black holes are identical and they are not spinning. It's a very simple case, but it's a nice movie. It was the first movie that we made from these simulations. This is by a team that I work with at Caltech, at my home institution, Cornell, and at the University of Toronto in Canada. In this movie, you will see at the top the two black holes. One is here, the other is off the screen. Can you see that well enough in the back? That's okay, good. And you'll see them as they would appear against a dark blue sky. Here you see the warped space as looking in from hyperspace, from outside our universe. The warped space of each black hole. The slowing of time is in the colors that are shown here, going from green to yellow to red down this funnel. And then the dragging of space into motion, because the black holes don't spin, it's only their motion of the black holes that drag space, shown by the white arrows. Down here is the gravitational wave shape for the waveform. It's very simple because these black holes are simple, they're not spinning. As this orbital motion goes on, we see we are moving through the waveform that would be measured on Earth when the gravitational waves arrive. You see the two black holes up here against the blue sky. You see them as seen by somebody in an external universe looking in. We have jumped over to here because it was rather boring. We will pause the movie as the black holes collide and merge, and then let the movie go on as the final merged black hole vibrates and settles down. This was a great triumph when this simulation was done, when we saw these results, because people had been working for 40 years to learn how to solve Einstein's equations on computers and to get computers that were powerful enough to do this. But now we are learning the interesting things about what happens when the black hole spins. The first thing I'm going to describe, again, these are new results in the last 2 years, is that in fact there are two kinds of vortexes of twisting space that stick out of a black hole. We discovered this in simulations, then we went back to Einstein's equations and understood it directly from the equations. If I have this woman who is hanging above the black hole, suspended above the black hole, Her feet are closer to the hole than her head, and so they are dragged into motion. Space is dragged into motion, and her feet with space, faster at her feet than at her head. So if you think about it, she looks down at her feet, and she sees her feet relative to her head is dragged around counterclockwise. If you think about it further, her feet looking at her head, see her head dragged counterclockwise. It's like if you take a wet towel and you wring water out of it. You can look from your left hand at the direction your right hand is going, and that is counterclockwise. You look at the right hand and the direction the left hand is going, that's counterclockwise. So you can wring a towel out in a counterclockwise way or in a clockwise way. There's two ways to wring a towel, twist a towel. Similarly then, we have a counterclockwise twist of space out the North Pole and a clockwise twist of space out the South Pole. And we see this in our simulations, and we can follow what happens. So suppose, for simplicity, I have two spinning black holes. They're going to collide head-on, for simplicity. And we have a red counterclockwise vortex of twisting space sticking out of this side, blue clockwise vortex. This one has the blue vortex up and the red vortex down. The two black holes, I'll show you a movie, but as a preview, they will collide, they merge. This is the merged horizon. You go beyond that point and you cannot get out. And I've colored the horizon blue where the blue vortex sticks out, red where the red vortex sticks out. There are now 4 vortexes of twisting space sticking out of this one black hole. And let's see what happens when the black holes collide and merge. So I will not show the vortexes, just the color of the horizon where the vortexes stick out. And I will pause the movie here and walk it through. As the black holes approach each other, they raise a tide on each other like a teardrop. They merge. We now have one black hole with 4 vortexes on it of twisting space. Now look at the upper right vortex. It's blue. Now watch what happens. The black hole vibrates. It oscillates. It went red, now blue, now red. It's a very strange thing we discovered in our simulations. When these vortexes discover each other, they feel each other, and each one grabs the other vortex and forces it to twist in its own direction. So they exchange twists. Initially, this one is twisting like that one like this, and then they have felt each other and they twist in the opposite way, then the opposite way. And with each oscillation, as this happens, something very weird occurs. Here is a moment when their vortex is sticking out of the black hole, the blue vortex, and the vortex lines, which represent the vortex of twisting space. This clockwise twisting space reaches out and around and goes back into the black hole on the other side. The red one comes out counterclockwise, goes around in the black hole on the other side. And with each oscillation, when they switch, the blue one has to come off and attach onto itself. The red one comes off and attaches onto itself, and then the black hole grows a new set of vortexes. And with each of those times when these vortexes come off and attach onto themselves, it creates a donut-shaped, a toroidal, a torus-shaped ring, like a smoke ring, of twisting space. It's a ring where space is twisting, and it is traveling outward from that black hole. And you get one ring after another ring of twisting space traveling outward. As it travels, these vortexes, they create things we call tendexes, which pull and squeeze, so that there is a pull of space, a stretching of space along the ring like this, and a squeezing of space along the ring like that. And this becomes then, this is what we call a gravitational wave. This gravitational wave travels out through the universe. It passes through Earth. As it passes through, it stretches in one direction, stretches you in one direction, squeezes you like that. It's a very small force. You don't feel it. You're not sensitive enough. And then it stretches you like this and squeezes you like that. At the same time, it's twisting you in other directions. So it would be rather unpleasant if it were a stronger force. But it's the thing that this black hole has created, this merged black hole, that you would feel. If the black holes are orbiting around each other when they collide, instead of creating a ring of shaped vortex, it creates spiral arms like water coming out of a turning sprinkler that become gravitational waves. These vortexes are so strong that they can take all of the material of a very dense star and twist it and throw it in new directions. Here I'm going to show a picture of a movie from a star, a so-called neutron star made of nuclear matter, which is orbiting around this black hole in this plane. The black hole is spinning around that direction. The star will be torn apart by the black hole, and then all of its nuclear matter will be thrown up into this plane by the twisting vortex. And so here we see the star goes around the black hole, 1.5 times heavier than the sun, is now thrown up like that by the black hole's twisting vortex. It's a very powerful vortex. This is nuclear matter, very dense, extremely hot. It emits things we call gamma rays and neutrinos, as well as gravitational waves. And so the community I work in is planning to observe this phenomenon with gravitational waves, with other forms of radiation, neutrinos, gamma rays. We call this multi-messenger astronomy. Each of these kinds of radiation is a messenger to bring us pictures of these violent, fantastic events occurring in the distant universe. So let me talk for a few minutes about the effort to detect the gravitational waves created when these two black holes orbit each other and collide, traveling across the great distances between the galaxies to come to Earth and bring us pictures of what is happening. Together with two colleagues, Ronald Drever at Caltech and Ray Weiss at MIT, I created a project to detect these gravitational waves. It's based on a detector that looks like this. We have 4 mirrors. Each mirror weighs 40 kilograms, so it's large, like this. Hangs by a quartz fiber, a quartz wire from an overhead support. They're separated by a distance of 4 kilometers. And this is along one direction. That's an orthogonal direction. This may be north-south and that east-west. When the gravitational wave comes past, it stretches these two apart, squeezes these together. The next half cycle of oscillation, it stretches these apart, squeezes those together. And the strength of this stretch and squeeze is about 4 times 10 to the minus 16 centimeters, when this separation is 4 kilometers. Now, that means that in order to see this, you must have a noise in your detectors that is below 1 times 10 to the minus 16 centimeters. The detectors, the way we detect this is we send a laser beam in. The laser beam goes back and forth between these mirrors and then comes back out. Back and forth between these mirrors, comes back out. And we use a technique called laser interferometry then to detect, to measure those motions. But we have to do this at this level of 1 times 10 to the minus 16 centimeters. Now, let me explain how small that is. So we begin with 1 centimeter. We divide it by 100, we get the thickness of a human hair. That's 100 microns. We divide by 100, we get the wavelength of the light that is used in these instruments. Divide by 10,000, we get the diameter of an atom. Divide by 100,000, we get the diameter of the nucleus of an atom. Divide by 1,000, we get the level of sensitivity of these instruments. This is incredible. In the early 1970s, I co-authored a textbook on general relativity in which I wrote an exercise that said, show why it is ridiculous. It was stupid to think you could ever detect gravitational waves by this method, because this effect is so small. And then I realized a few years later that it would be possible, and I have spent much of my career since then helping make it possible. So it is remarkable to achieve this kind of sensitivity. We have built, my colleagues and I have built an observatory system with those kinds of so-called interferometers to detect gravitational waves in Hanford, Washington, near Seattle, in Louisiana, near New Orleans, in Hanover, Germany. And this Hanover instrument, and the project is largely joint US, Germany, and the UK. There's a project called Virgo with one such instrument in Pisa, Italy, that is a joint French, Italian, Dutch project. The Japanese are preparing to build a similar instrument in Japan, and we are planning to move one of our 3 instruments to India over the next several years. So we have a very large worldwide network. We need this because these signals are so very small, and we do not understand the noise in these instruments very well. So we need to see similar signals in many different instruments, widely separated, to believe that we are really seeing these gravitational waves. We need also this network to determine the direction toward the source and to extract these wave shapes, the so-called waveforms that carry the information. This is a picture of our instrument in Hanford, Washington, Livingston, Louisiana. LIGO is now a collaboration of 850 scientists at 75 institutions in 13 nations. When we proposed to build this, after working for 6 years on preparing the plans, we proposed in 1989 we would do this in 2 steps. We would build an initial set of interferometers to look for these waves at a sensitivity where it is plausible but not likely we would see them. And then we would improve these, making advanced interferometers at a better sensitivity where it is likely we would see many waves from many sources. We had to do this in 2 steps because the technology is so new and so difficult. We had to develop experience with the initial detectors in order to be successful with the advanced detectors. The initial ones were built, they operated from 2005 to 2010. They could have seen black holes colliding out to 300 million light years. This is a region inside which there are about 10,000 galaxies like our own. Nothing has been seen as yet. We have some interesting limits, but we've not seen any waves. We didn't expect to see any. We would have to be lucky. The advanced interferometers, we began installation October 2010, nearly 2 years ago. This is a long process. These are very complicated instruments to install and then to commission, that is to debug, to bring to their sensitivity. We should be seeing gravitational waves and doing rich science by about 2017. So we are within about 5 years of the big payoff from a field where we've been working for several decades. These advanced detectors are remarkable, among other things, because we now will be measuring the motions of these 40-kilogram mirrors to a precision, which is the precision at which these 40-kilogram objects cease to obey the laws of classical mechanics and begin to obey the laws of quantum physics. Always in the past, when we study quantum physics, we see quantum effects. We see uncertainties. You measure something and you always perturb it. You can never say precisely where things are, only the probability about where they are. We see these quantum physics effects in atoms and in molecules, but not in human-sized objects. In LIGO, for the first time, we will see them in human-sized objects, and in order to deal with that, we have had to build into these advanced detectors, quantum non-demolition technology. This is a fancy word to simply say we must be able to measure the gravitational waves in the presence of quantum uncertainties without demolishing the signal information. We must get the signal information through a device that is the size of you and me almost, that is behaving quantum mechanically without demolishing the information. This is a branch of a new, this is one branch of a new field of high technology called quantum information science. Quantum information science also includes quantum cryptography, quantum computing, and quantum non-demolition. So it's what is going to be very important in technology over the coming few decades. And we have had to build this in from the beginning. My own research group began working on these quantum non-demolition techniques together with the experimenters. My group is a theory group in 1980. So we've been planning for this for 30 years. We will also, a little later, look for gravitational waves with detectors that have, instead of mirrors hanging by wires, 3 spacecraft floating out in space, in interplanetary space, separated by a distance of 1 million kilometers. They track each other with laser beams. The gravitational wave comes along and pushes them together and apart. We see this in the laser signals. This is called ELISA, the European Laser Interferometer Space Antenna. It's being done by ESA. And because these masses are so far apart, they can see gravitational waves of very long wavelengths. Wavelengths that are the size of the distance between the Earth and the Moon or the Earth and the Sun. And these are produced by giant black holes in distant galaxies. And so this is a very different kind of black hole. Huge black holes we study with these instruments, small black holes with the instruments on the surface of the Earth. A test of the technology for LISA will be done in 2014. The so-called LISA Pathfinder mission will fly, flown by the European Space Agency. And then about 14 years later, LISA itself. So this is still quite some time off, but it's very exciting. It will teach us different things about the warped space and time than LIGO does. For example, we will, with LISA, be able to watch the gravitational waves from a small black hole going around a very large black hole. The small black hole, in traveling around from here, will go around and around 100,000 times before it falls through the horizon of the big black hole. And that's 100,000 trips over a period of a year. It will emit a very long wave with exquisitely accurate information that is a map of the space-time geometry of the warped space and the warped time of the whirling space of the big black hole, the small hole experiences as it goes around. And so our goal is to detect these waves, measure the waveforms, and extract the map so we can make very accurate pictures of black holes. Just to give you some numbers, then this big black hole might weigh 1 million times as much as the sun, the small just 10 times what the sun weighs. This distance here across may be 5 million kilometers. 3 billion light years from Earth. This is out near the edge of the observable universe. LISA, 1 million kilometers on a side, extracting the information, building a map of the warped space and time of the big black hole. And what if the map is not that of a black hole? Well, then we may have discovered a new kind of object that's made from warped space and time, a new inhabitant of what I like to call the warped side of the universe. One possibility is an object made of what we call cold dark matter, which I won't go into. Michael Turner did talk about this here several years ago. So, for example, something called a boson star, whose warped space might look like that, for example. Or a singularity of infinitely warped space and time, where you would die, be torn apart at the center. Singularity that does not have a black hole around it, does not have a horizon. We call this a naked singularity. Can naked singularities actually exist? The establishment, that is, the people who really set the direction for physics, has an answer: probably not. This is codified in Roger Penrose's cosmic censorship conjecture, his guess, educated guess, that all singularities except the Big Bang are hidden inside black holes. That is, they're clothed by horizons. You cannot have naked singularities. And so Stephen Hawking, who, like Roger Penrose, the two great British physicists in my field, believe in cosmic censorship. Stephen made a bet with John Preskill and me at Caltech a few years ago, well, 1991, so 21 years ago, about this. The bet says, whereas Stephen Hawking firmly believes that naked singularities are an anathema, that is, that they are terrible, they're very bad things, and they should be forbidden, prohibited by the laws of classical physics, whereas Preskill and Thorne think that these naked singularities should be thought of as quantum gravity objects governed by the new laws of quantum gravity, and they might exist unclothed, not hidden by horizons, for all the universe to see. Therefore, we make a bet, and this is some technical words designed to protect Hawking's side of the bet. Hawking and I are very close friends. I can be very irreverent about him, so he needed some protection. The loser will reward the winner with clothing to cover the winner's nakedness. Clothing is to be embroidered with a suitable concessionary message. This was the occasion about 10 years ago when Hawking conceded the bet. He agreed he was wrong and that we were right, that you can have naked singularities. But he did not do so graciously. He gave us a T-shirt to hide our nakedness. Now, on the T-shirt, there's a picture of a woman hiding her nakedness with a towel that says, "Nature abhors." Nature very much dislikes a naked singularity. Hawking agreed that naked singularities could occur, but he insisted they will not occur because nature dislikes them so much. Let me be more precise. Why did he concede? There was a numerical simulation on a computer in which gravitational waves were sent in toward a center, imploding from all directions. And as they went in, this was done by Matt Choptuik, a young physicist at the University of Texas at the time. As they went in, the gravitational waves interacted with themselves and created almost a bubbling, a foaming, like the bubbles in a clothes washing machine when you put too much soap in. So a frothing, and then right at the center, there was created at the very end a tiny, very, very small naked singularity in this simulation. Singularity was very small and it lived for a very short period of time, but it was enough to force Hawking to concede. However, if in the simulation, if Choptuik increased the strength of the wave slightly, instead of a naked singularity, he got a black hole. If he made it slightly less strong wave, there was nothing left at the center at all. The waves went in and came back out. So he had to very carefully choose how strong the wave was in order to get a naked singularity, and nature doesn't work that way. Nature makes random choices of things. And so it's very unlikely that nature has carefully chosen strengths of things to make naked singularities, Hawking. And that's why Hawking insists nature abhors, dislikes naked singularities. So we have a new bet as to whether or not this does occur in nature. We will try to settle the bet by looking for these naked singularities with Lisa, doing mapping of the gravitational waves and seeing if we see a map of an object that is a naked singularity. I want to say a few words about wormholes. This is a topic that I worked on. I initiated research on wormholes in the modern era back in the late 1980s. A wormhole is an object that has two mouths. I may have one mouth over here. It will just look like a sphere. Another mouth over there. If I look in here, it will say it may look like a crystal ball. I look in, and light travels from that mouth through to me. So I see an image here of what is at that sphere over there. I call it a mouth, but it's a sphere in shape. And if I go over there and look, light comes from this sphere through the wormhole, and I see it over here. So if I have such a wormhole, a mouth in my office and the other mouth of the wormhole outdoors, then I look in the mouth in my office, and I see a picture of the countryside around the other mouth. If I look in this mouth that's sitting out in the countryside, I see a picture of me, I see a picture of whoever is in my office. I can travel into this mouth and come out of that mouth. The connection may be very short. The connection is not part of our universe. It's going through hyperspace, through higher dimensional space. You can understand this by thinking about real wormholes in apples. Our universe is like the surface of the apple. It may be flattened very much, so this wormhole is very short through from one side to the other. If you have two ways to get from here to there, through the external universe or through the wormhole. The wormhole is very short. Wormholes are allowed to exist by Einstein's general relativity theory. But we think they do not exist naturally. There's been a lot of research on this in recent years. We don't know whether an advanced civilization can make them, but it would be very good if they could, because they could be used for very rapid interstellar travel. That's how they're used, of course, by Hollywood in movies such as Star Trek. And there is an issue of how you hold them open, because a wormhole naturally wants to squeeze off. Its gravity pulls it off, so it collapses and you can't travel through. It turns out we've been able to show that the only way to hold the wormhole open so you could travel through it is you have to put something inside the wormhole that anti-gravitates. Instead of pulling, it pushes. And this has to be something that has what we call negative energy, less energy than zero energy. You can borrow from the bank and have a negative account, but you have to pay it back soon. Quantum physics says you can borrow energy at this location from another location in space, and thereby have negative energy at the other location. You can feed energy from one location to another, but you can only do it briefly. You have to return that energy very quickly. And so our best estimates from work with quantum physics is that you can't get enough energy for long enough, that is enough negative energy for long enough to hold a wormhole open. But we don't know for sure. The answer has to come from these laws of quantum gravity that we don't yet fully understand. One other topic before I move into my closing, and that is, if you do have a wormhole, again, this is research that I did with students of mine in the early 1990s, it turns out you can turn that wormhole into a time machine if you have a wormhole. It's rather simple in principle, not so easy in practice. We don't have the technology yet. But you keep one mouth here in my office at Caltech, and I send these pictures are myself and my wife 20 years ago when I had more hair. And so I'm in my office. My wife goes on a rocket trip and goes down into orbit around a black hole where time flows slowly. She ages by 1 day, while I age by 10 years. So I'm now 10 years older than she is. And we can look at each other and see I'm 10 years older than she is. But during that entire time, we may hold hands through the wormhole. My hand is going in, hers is. We are actually holding hands. And looking at our hands, we see we age at the same rate. So it's very weird. Looking through the wormhole, she sees me the same, having aged only 1 day. But looking through the external universe, she sees that I have aged by 10 years. How is that possible? The answer is the wormhole has become a time machine. If she goes through the wormhole, she travels through the wormhole and goes back in time by 10 years to where I was truly young. And just by putting one mouth of the wormhole near a black hole and waiting a short time, the whole wormhole becomes a time machine. However, we also discovered, this is work I did with a postdoctoral student, that at the moment when something can first travel backward in time, radiation travels into her mouth, backward in time, out of my mouth, and returns, arriving back at its starting point at the same moment as it started. You begin with one particle of radiation, makes the trip. Now you have two at the same location in space and time. Those two make a trip. Now you have four. From just one particle of radiation, you can wind up with infinitely strong radiation, which will destroy the wormhole at the very moment when you have turned it into a time machine. So the calculations suggest. When we look more carefully at the calculations, we see that just when the explosion becomes strong enough to destroy the time machine, the laws of nature we're using for the calculations fail, and we need the new laws of quantum gravity to tell us what happens. So the laws of quantum gravity hold this answer to whether you can make a time machine, what happens inside a black hole at the singularity, and also what happens in the Big Bang singularity, and that's where I want to wind up. When we look out on the sky in all directions, we see something called the cosmic microwave background radiation. It's photons, particles, the same kinds of particles as light are made from. And they are left over from the Big Bang, and they bring us a picture of what the universe looked like when it was about 100,000 years old. But earlier than 100,000 years, I'm going back in time and out in distance here now, earlier than 100,000 years age, the universe was so hot and so dense that that photons could not propagate. They were absorbed, they were scattered, they lost all their information. So we can, with photons, light, microwaves, electromagnetic waves, we can only explore the universe after the first 100,000 years. Neutrinos are very highly penetrating particles, and they could be used if we have the technology to find them from the Big Bang to explore the universe when it is 1 second old. Gravitational waves are the only form of radiation that penetrates so well through hot, dense matter that it can travel from the Big Bang, birth of the universe, to us without being absorbed or scattered. So they are our only way of directly observing the birth of the universe. We look out, see gravitational waves coming from very far away. That means they were emitted very long ago, so long ago that we can actually see the birth of the universe if we get our gravitational wave detectors to be sufficiently sensitive. And they can explore the first 1 second of the life of the universe, in which there's a lot of violence. There's the Big Bang birth of the universe itself. Theory says that in the earliest moments of the universe, some of the strings that are the fundamental building blocks of nature, we think, this is part of the tentative laws of quantum gravity, some of these strings may have been stretched to become like giant rubber bands, giant strings reaching across the universe, like a giant violin string reaching across the universe. And there may be a number of these, and when they pass through each other, run into each other, they reconnect, and you get a string with a bend in it. And that bend travels at the speed of light, producing gravitational waves, according to the prediction. So with LIGO, we are looking for these waves at this moment that come from the earliest moments of the universe, from these big strings created from the tiny strings that are part of the new laws of quantum gravity. When the universe was 1 trillionth of a second old, it was so hot that the energies of the particles were similar to the energies of particles in the Large Hadron Collider at CERN in Geneva that are being used today to explore fundamental physics. And that was the era in which the electromagnetic force was created. The electric force and magnetic force didn't even exist according to theory before that. We would like to see the electromagnetic force being born at that early moment of the universe. And we expect to be able to see it, if we're lucky, because the force is born through what's called a phase transition, like water condensing out in a cloud to form droplets. So you get a droplet in which the electric and magnetic force exist inside a bulk region where they don't exist. These droplets collide and merge, and in the collision they emit gravitational waves, which are at the right frequency and strength to be seen by LISA. So we will use LISA to try to watch in the earliest moments of the universe, when the universe is 1/1 trillionth of a second old, watch the birth of the fundamental forces. And finally, the universe may, in fact, be a three-dimensional surface in four-dimensional space, or in a higher dimensional hyperspace, and it may have formed wrinkled like this piece of paper. And as the universe expands and time passes, adjacent regions discover there is a wrinkle in between them. And there's a great tension, like in a drum head or in a violin string, that causes the universe to straighten out. To remove the wrinkle, the universe vibrates in the higher dimensional space. And those vibrations we see as gravitational waves. And so this is a kind of a great surprise that might come from looking at the earliest moments of the universe, to actually see the evidence that our universe does live in a higher dimensional space through this weird kind of a process. So let me conclude. We remain, although I've told you a lot of strange things, we still remain quite ignorant about what I call the warped side of the universe, things that are made from warped space and time. Does a black hole have the precise shapes of warping that general relativity predicts? What happens when black holes collide? The Big Bang singularity, what are its details? What happened before the Big Bang? Is our universe truly a three-dimensional membrane, or brain as the physicists say, living in a higher dimensional hyperspace? What other objects reside in the warped side of the universe? What other objects are there that are made from warped space and time? Boson stars, cosmic strings, wormholes. Are time machines possible? Singularities, what are their structures? How do they behave? The singularity at the core of a black hole, the Big Bang singularity. The answers are going to come from a combination of theory and computer simulations and gravitational wave observations. And so the coming several decades will be, I think, even more exciting than the last two in which I've been one of the lead participants. Thank you.